According to the laws of physics, you should not exist, not as a metaphor, not philosophically, but as a measurable outcome of the early universe. The equations say that matter and antimatter should have been created in equal amounts. When they meet, they annihilate. If the rules were followed exactly, everything would have cancelled out, leaving a universe filled with light and nothing else. And yet, you are here. This is not a speculative problem. Antimatter is real, measurable, and routinely produced in laboratories. When it comes into contact with matter, the result is immediate and exact. Total destruction on both sides. No residue, no exception. The same rules that govern particle accelerators today governed the universe at its birth. By those rules, long-lived matter should never have survived. For decades, physicists assumed the answer must be hidden somewhere far away. Perhaps antimatter was pushed beyond our reach, trapped in distant regions of space. Perhaps entire galaxies made of antimatter existed beyond our view. But the universe has been observed carefully, and it has remained silent. Everywhere we look, matter dominates. The imbalance is not subtle, it is overwhelming. What makes this unsettling is that the contradiction is not abstract. It is personal. Your body, the earth, every atom in the room represents a violation of what symmetric laws predict. Somewhere, something broke the rules just enough to let matter win. Physicists have measured, tested, and searched for that break for generations. What they have found so far is not an answer, but a growing problem. The rule at the center of this problem is symmetry. In modern physics, symmetry is not aesthetic. It is law. For every particle of matter, there exists a corresponding particle of antimatter with opposite charge and identical mass. When created, they emerge as pairs. When they interact, they annihilate with perfect efficiency. The equations describing this behavior have been tested repeatedly and have never failed under controlled conditions. This symmetry is not limited to rare processes. It applies to electrons, protons, muons, and their antiparticles. It governs nuclear reactions, particle collisions, and radioactive decay. The mathematics does not allow preference. Matter is not favored. Antimatter is not secondary. They are treated as equals by the laws themselves. When physicists reconstruct the conditions of the early universe, this rule becomes unavoidable. Extreme temperatures and energies would have produced matter and antimatter in enormous quantities. They would have collided constantly, erasing each other in flashes of radiation. As the universe cooled, annihilation should have continued until almost nothing remained. A slight imbalance could leave a trace, but not enough to build stars, planets, or observers. What we see instead is a universe built almost entirely of matter. Antimatter exists only fleetingly, created artificially, or detected indirectly. The ratio is not close, it is catastrophically skewed. For every billion particles of antimatter that should exist, there are billions of particles of matter left over. The symmetry rule predicts cancellation. Reality delivers survival. This is not a matter of interpretation. The imbalance can be calculated, measured, and expressed numerically. The known laws of physics do not produce the required excess. They fall short by orders of magnitude. Even when all known effects are included, the math refuses to reach the observed outcome. At this point, physics reaches an uncomfortable boundary. The rules that successfully describe everything else do not explain why anything exists at all. The paradox is not that matter behaves strangely, but that it behaves at all. According to the symmetry that governs particles, the universe should have erased itself cleanly. It did not, and current theory cannot say why. The first escape route was distance. If matter and antimatter were created equally, perhaps they were simply separated before annihilation could finish. Entire regions of the universe might be made of antimatter, far beyond our reach. The idea was attractive because it preserved the symmetry. The rules would remain intact, and the imbalance would be only apparent, not real. This possibility came with a clear prediction. Where matter regions meet antimatter regions, annihilation should occur on a colossal scale. The boundaries would glow with distinctive radiation signatures, sharp and unmistakable. Telescopes were pointed outward, not in hope, but in expectation. If antimatter was out there, the universe would be loudly advertising it. It did not. Observations of galaxies, clusters, and cosmic background radiation showed no such signals. The sky was quiet in exactly the wrong way. The absence was not local or patchy. It was uniform. Matter dominated everywhere that could be measured, in every direction and at every accessible scale. Physicists pushed the search further. They examined high-energy cosmic rays, looking for antimatter nuclei that could only originate from antimatter stars or galaxies. None appeared in sufficient quantity. The detections matched secondary processes, not primordial sources. The universe was not hiding antimatter poorly. It was not hiding it at all. Even gravitational behavior offered no refuge. Antimatter, if present in large structures, would bend light and influence motion just like matter. Those signatures were also missing. The cosmic web traced by gravity told a consistent story. The mass shaping galaxies and clusters behaved exactly as matter should. With each observational check, another exit closed. Antimatter was not elsewhere. It was not waiting beyond a horizon. The universe itself had testified, repeatedly and consistently. The imbalance was not a matter of location. It was built into reality from the beginning. When the universe refused to provide an external hiding place, attention turned inward. If matter and antimatter were not separated in space, then the difference had to be written into the laws themselves. This was a more dangerous idea. It meant that symmetry, long treated as absolute, might be only approximate. Physicists had encountered broken symmetries before. In certain processes, nature distinguishes left from right or past from future. These violations were not philosophical curiosities. They were measured effects, recorded in laboratories, and incorporated into accepted theory. The question was whether any of these asymmetries could be responsible for matter's survival. The first candidate was charge symmetry. If particles and antiparticles behaved even slightly differently during decay, that difference could accumulate. Experiments began searching for tiny imbalances in how unstable particles transformed over time. Most results confirmed symmetry with unsettling precision. The universe appeared stubbornly fair. Then came a crack. In the mid-20th century, physicists observed that certain decays did not respect combined symmetries involving charge and spatial orientation. This phenomenon, known as CP violation, was small but real. Matter and antimatter were not perfect mirrors after all. For the first time, the laws showed bias. The discovery was unsettling precisely because it was subtle. The violations appeared only in rare particle interactions under specific conditions. They did not overturn existing theory, but they bent it. The rules still worked, but no longer with perfect balance. This shift changed the problem's tone. The question was no longer whether asymmetry existed, but whether it existed in sufficient strength. If CP violation could tip the scales early enough and often enough, matter might gain a foothold before annihilation completed. Hope entered cautiously. The laws were no longer entirely fair, but hope in physics is quantitative. It demands numbers, not narratives. The next step was to calculate whether this known bias could account for a universe made almost entirely of matter. At first glance, CP violation looked like the long-awaited solution. It was real, measurable, and already embedded in the equations describing particle behavior. For the first time, physics possessed a mechanism that treated matter and antimatter differently. The symmetry that once guaranteed mutual destruction was no longer exact. The imbalance, however small, finally had a name. Physicists began translating this bias into numbers. They modeled the early universe, inserting known CP, violating effects into simulations of particle creation and decay. The logic was straightforward. If matter decayed just slightly differently from antimatter, the difference could compound as the universe cooled. Survival would no longer be forbidden, only unlikely. The results were disappointing. The asymmetry produced by known CP violation was far too weak. It generated an excess of matter, but one that was vanishingly small compared to what is observed. The universe we see requires an imbalance many orders of magnitude larger. The math refused to stretch that far. Attempts to amplify the effect ran into constraints. Increasing CP violation arbitrarily would break other predictions that experiments have already confirmed. Particle lifetimes, decay rates, and interaction strengths are tightly measured. Any adjustment large enough to explain cosmic matter abundance would immediately contradict laboratory data. The near answer became a trap. It explained just enough to be tempting, but not enough to work. CP violation was not wrong. It was insufficient. The mechanism existed, but it lacked the power required to shape the universe. What once felt like progress now sharpened the mystery. This failure carried psychological weight. Physics had found a crack in symmetry, then discovered it was too small to matter. The laws were biased, but not biased enough. The universe had cheated, but not in any way that current equations could justify. The paradox deepened. Matter's survival was no longer impossible, yet it remained unexplained. The explanation was not missing entirely. It was incomplete, and that incompleteness forced physicists to confront a more unsettling possibility, that something fundamental was still absent from the theory itself. With theory unable to bridge the gap, attention returned to experiment. If the laws hinted at missing ingredients, perhaps precision measurements could expose them. Physicists began testing matter and antimatter directly, not in cosmic averages, but in controlled environments where even tiny differences could be detected. One approach focused on gravity. If antimatter responded differently to gravitational fields, even slightly, that difference could reshape early cosmic dynamics. Experiments were designed to trap antimatter atoms and observe their motion in isolation. The setups were delicate, shielded from interference, and pushed to technical limits. The results were unsettling in their normality. Antimatter fell exactly as matter did, within experimental uncertainty. No preference, no reversal, no hidden asymmetry large enough to matter. Gravity, at least as measured, treated both sides equally. Other tests examined spectral lines, magnetic moments, and decay behavior with increasing precision. Each measurement tightened constraints. Each null result removed another potential explanation. Antimatter continued to behave like an obedient mirror, even where deviation was hoped for. Silence became a result in itself. The absence of anomalies was no longer reassuring. Every confirmation of symmetry made the cosmic imbalance harder to explain. The universe had broken the rules somewhere, but refused to reveal where. By this stage, physics had reached an uncomfortable position. Experiments were precise enough to detect deviations, yet none appeared. Theory predicted imbalance too weak to matter. Observation insisted that matter dominated completely. The gap between knowledge and reality remained, clean and unresolved. Silence, once a sign of success, now felt suspicious. As traditional tests returned only confirmation, some physicists began pushing beyond passive observation. If the imbalance would not reveal itself naturally, it might need to be provoked. New experiments were proposed that treated antimatter not as a fleeting curiosity, but as something that could be stored, transported, and manipulated over time. This required engineering at the edge of feasibility. Antimatter annihilates on contact with ordinary matter, so containment demanded near-perfect isolation. Magnetic and electric traps were refined to hold antiatoms suspended in vacuum, removed from walls, fields, and stray particles. Every second of confinement was a technical achievement. The risks were not theoretical. A containment failure would destroy the sample instantly, erasing weeks or months of work. Yet the quantities involved were so small that danger to surroundings was negligible. The real cost was informational. Each lost sample meant lost opportunity to test subtle effects that might appear only after extended observation. Some proposals went further, transporting antimatter between facilities, rotating experimental frames, and subjecting antiatoms to varying gravitational orientations were all considered. These were not reckless ideas, but they signaled growing urgency. Physics was no longer waiting for anomalies. It was trying to force them into view. Despite the audacity, results remained stubbornly ordinary. Antimatter continued to obey known laws with unsettling discipline. No unexpected drift, no delayed decay, no hidden asymmetry emerged under stress. The experiments demonstrated ingenuity, but not resolution. What these efforts revealed most clearly was desperation without panic. Physicists were not abandoning rigor, they were exhausting it. When engineering becomes radical while conclusions remain cautious, it signals proximity to a conceptual boundary that tools alone may not cross. With experiments narrowing the possibilities, theory began to approach a cliff. The remaining options were no longer small adjustments, but changes that would ripple through the foundations of physics. One such pillar is CPT symmetry, the principle that physics remains unchanged if charge, spatial orientation, and time are all reversed together. It is woven deeply into quantum field theory. If CPT symmetry were violated even slightly, the consequences would be profound. Matter and antimatter could differ in mass, lifetime, or fundamental behavior. Such a violation could generate the imbalance required for matter to survive. But CPT symmetry is not an optional rule. It underlies the mathematical consistency of the entire framework. Breaking it risks unraveling more than it explains. Other ideas introduce new forces or hidden particles that interact asymmetrically. These hypothetical influences would have to be subtle enough to evade detection, yet powerful enough to dominate the early universe. Some models propose unstable vacuum states, or fields, that briefly tipped the balance before vanishing. Each possibility solves one problem, while creating several others. What unites these ideas is their cost. Accepting them would mean that some of the most trusted assumptions in physics are incomplete, not wrong, but provisional. The universe would no longer be governed by perfectly neutral laws, but by ones that quietly favor existence over symmetry. At this edge, physics pauses. The data does not demand a specific answer, only a decision about how far theory is willing to bend. The mystery has shifted from observation to interpretation. What remains unresolved is not whether something is missing, but how fundamental that absence might be. The problem has never been that physics lacks detail. It has detail in excess. Equations describe particles to astonishing precision. Experiments verify those descriptions repeatedly. And yet, the most basic fact of all remains unexplained. Matter exists in a universe where it should have erased itself completely. What has been ruled out is as important as what remains. Antimatter is not hiding beyond the stars. Known symmetries are not perfectly fair, but they are not biased enough. Precision experiments have searched for loopholes and found only consistency. The imbalance that allowed everything to exist does not appear where physics knows how to look. What remains disturbing is the scale of the mismatch. The universe did not just lean toward matter, it committed to it overwhelmingly. That commitment is written into every atom, every structure, every observer. It is not an edge case, it is the default state of reality. Physics now sits with an open investigation rather than a failure. The rules work, but they are incomplete. Something influenced the earliest moments of the universe and then disappeared, leaving consequences without a clear cause. Whether that influence was a hidden field, a broken symmetry, or a deeper structure still unknown, remains unresolved. This is not a mystery waiting for belief. It is waiting for measurement, for theory, for courage. The equations insist the universe should be empty. The evidence insists otherwise. Between those two statements lies the unanswered question that continues to drive the search. You are not just observing the anomaly. You are made of it. The universe you inhabit is the data that should not exist, and the reason it does remains an open problem.